Did someone just say summer school and math? Nah, you're likely passing. So don't worry too much about summer school unless you want to upgrade or unless you want to reach ahead into some grade 12 stuff. But today, that's not our question, everyone. I want to thank everyone for showing up for their math learning. And we're going to take a very quick look at this topic. When you've got this situation, you want to find missing angles in right triangles, and you've been given two side lengths. Okay, this is generally the magic amount of information you need to have a solvable triangle. So, suppose we had this situation. We're given two angles in the triangle. Go ahead and find the third angle. So, what does that make that one? So, that's very good. It is indeed 61. So, this is 61 degrees. When you've got these, you can label your triangle ABC. And you can use this formula A plus B plus C equals 180 and rearrange and solve. And if you know to get 61 there, that's great. The other thing that you can remember is these two angles in a triangle, the ones opposite the right angle, always add up to 90. That's only true in right angle triangles, but right angle triangles are going to be a lot of the triangles you work on. So getting good at that is a good skill. Now, suppose I told you that the hypotenuse was 10. As a warm-up, just to review what we did Friday, how would you solve for me little side B and little side A there? About how big do you think B is going to be? Start with a guess. B is going to be greater than how many? Could B be like 1 or 2? You said 4? Yeah, is that what you said?
So it would be more than 5.
More than 5?
This doesn't is flat or something. They both have to be.
Yeah, A and B would have to add up to be more than 10.
Yeah.
So if B is like around 5 and A would be like, I don't know, what do you think? Like around 7 or something?
Yeah, that's what I was thinking.
Start with some guesses. Okay, and if you're slow to guess, like people are kind of slow to shout out numbers here, I'm going to take a number like 1 or a number like 9 as a guess. A number like 12, and I'm going to say, can it be longer than the hypotenuse? Your guesses will get better. It's gonna improve, but just have that as part of your problem solving. And then let's solve for B first. About how long? What trigonometric ratio can we use to solve for B? Using either 61 or 29. I heard someone say sine. What angle would I use if I'm using sine here?
29.
Yes, so sine theta is equal to opposite over hypotenuse. Write these out every time. It's very good for your memory and good for your math communication. And then you write out sine 29, and we find the opposite of 29 is b. So we're going to have b on 10 is the hypotenuse. Solving that one, we're just going to isolate b by multiplying both sides by 10. So we choose to do that so that we get the line 10 times sine 29 equals b, because those canceled. And then we punch that. Punch that on our calculator. 10 multiplied by 29, but I take the sine of it. Oh, it looks like sine 29 is very close to 1/2, just a little less than 1/2, 0.484. Okay, so we get 4.8, 4.848. So we're going to call b is equal to 4.8. We're very pleased with that. We have solved for that side. At this point, we've actually got options. Okay, we have two sides, so we could use Pythagorean theorem to solve for that one. But it would likely be simpler and easier and more direct. You could do cosine 29 or sine 61 and do the same process to solve for A. We're not going to do that one right now, but that's how we would do it. Sine 61, we could use sine 61 here because we know that this angle up there is 61 degrees. And sine 61, let me just get a good highlighter color. Sine 61 would relate the opposite angle to the hypotenuse. So we could work that way. Or we could use cosine 29 is the adjacent and the hypotenuse. So we'd have both of those options. Or you could do c squared equals a squared plus b squared. And you could use Pythagorean theorem. Trigonometry is built from the Pythagorean theorem. So all of these methods are at their core the same, but they're very different on your calculator. So you choose the ones that are going to give you the best accuracy or that you know you can make the fewest mistakes doing. Oh, let's keep going. When we have two sides and a right angle, okay, we need that for this to be true, it is possible to solve for the other angles using SOHCAHTOA. So in this case, suppose we're interested in finding theta. What trigonometric ratio would relate these two sides through theta? Sine, cos, or tan? It involves the hypotenuse, so it's not tangent. Tangent is the weird cousin that doesn't use the hypotenuse. Tangent's got his own stuff going on, though. Tangent's a pretty cool dude. But sine and cosine are like the siblings that are really close. This one is cosine, and you are correct. It relates, so we say cos theta, write these out, equals adjacent divided by hypotenuse. And then we go ahead and sub in. Cosine theta equals 9.7 divided by 17. The centimeters are going to cancel out. I could write centimeters, but they would cancel. If you had mixed units, that would be a gross type of problem where one is in inches and one is in centimeters. You'd have to convert. Now, we use this inverse operation here. Take the inverse cosine of both sides, or simply write on the next line, theta is equal to cos inverse, put it in brackets, 9.7 on 17. Why do I need to put that in brackets when I punch it on my calculator?
Because we're multiplying.
9.7, this would be divided by 17. If we don't do that, we'll be like taking the cosine inverse of 9.7, and that's not possible. That won't work. It will not function. So this is what we call the argument of the cosine inverse. That's the thing that that math function is going to be its input. So we want to make sure it takes the whole input and uses the whole input for cosine inverse. So when you type that on your calculator, put that in brackets. And then this is what it would look like if I do it. I do 9.7, I divide by 17, I get this decimal number, and then I take the cosine inverse of that decimal number, and I get 55. So theta is equal to 55 degrees. What a nice surprise. This problem was prepared by probably a Fibonacci lover like myself. And then we compare that to our guess. Folks, we forgot to guess. We're rushing. Okay, we want to look at that and say, okay, that's going to be like, I don't know, in and around 60 degrees it looks like. And then turns out, yeah, it's very, very close to 60 degrees, 55 degrees. Okay, let's keep going. What would you guess theta is in this case over here? Ballpark it. Use your mental protractor to figure that out. Give me a guess.
50.
So I got guesses like 40, I got guesses like 50. I would guess a little more than 40 since this looks like it's more than 45 degrees. So we might be thinking like somewhere between 40 might be a lower bound, and then something like, I don't know, could be 65, somewhere in there. Just have a range and then process it. What ratio is going to relate this side to this side through theta there? Which ratio are we using? Sine, cos, or tan? Yeah, we're going to use sine. Sine law is tomorrow's topic. Sine law doesn't involve right angles, but you can use it here, but you wouldn't want to. So we're going to write it out. Sine theta is equal to opposite over a hypotenuse. Well chosen. So then sub in. Sine of theta is equal to, and you can write 12 is your opposite on 21. if you want, go ahead and reduce that when you see it. Does that fraction reduce? To what?
When you say reduce, you mean simplify, right?
Yeah. I mean, we could tell the calculator 12/21 and we wouldn't be wrong, but punching 4/7 is a little better. And just because we do this as a habit, you want to have this habit of always reduce your fractions. It's just good practice. So then, our next line, you can just simply write theta is equal to sine inverse of 4/7. But I always have the same starting place for all of these problems. It's copy out the relevant formula and then sub in and rearrange. That way my algebra muscles are getting strong and I'm seeing the connections between the different methods. So, punch that on the calculator. For me, that looks like this. Because my calculator, I have to have, if I just do sine inverse here, it'll do it of whatever's on the calculator. So I need 4 divided by 7 equals, so this is another way you can do it, is equals, and then say sine inverse of the answer you just got, if you don't want to use the brackets on your calculator. So I take sine inverse of that. It's almost always second function on your calculator. This tells me it's 34.8. Well, that's not what I guessed. 34.84. So about 35 degrees. 21/12. Oh yeah. Oh wow, the diagram is really bad. So this is a good lesson. Don't trust diagrams. This side's actually the second longest side in the triangle. Wild. Okay, now we know. So, diagrams are there so you get your algebra set up right. So the algebra is set up right here. The diagram is not there so you can measure it and think, oh, it's about this much. Unless it's a 2-scale diagram, that technique doesn't work. It's only there so your algebra ends up organized in the right way. You know which one is the opposite, which one is the adjacent, which one is the hypotenuse, and you're using the correct math functions. So that's a good lesson about diagrams there. Over here, it's asking us to solve for 2 angles, but to be honest, it's pretty well the same. I'll just run this one really fast. Sine of beta is equal to 5/34. Yes, the Fibonacci lover made this one. So I do beta is equal to sine inverse 5/34. Crunch it. And we find that that's about 8.5 degrees. We'll keep 8.5. If I know that this is 8.5 degrees, which would be, to be honest, a little bit smaller than what I would have guessed, but hey, we're all learning. Now I'm just going to use the fact that these two add to 90. So that makes this one down here 81.5 is that one. Okay, based on our guess. But we could have also solved for alpha this way. Sine alpha is equal to, sorry, not sine, cosine. Cosine of alpha is equal to 5/34. So punch that. 5 divided by 34 equals, take the inverse cosine of it, 81.5. Just like what we got when we used adds to 90. So both methods are fine. Whatever you're comfy with. Another thing that you're going to be asked to do is create your own diagrams. That's kind of where this can step up into blue square, is where you're given a bunch of information and you need to know how to arrange it and put it together into a diagram, particularly adapting to different situations, different application problems, for example. In this case, we want to be able to draw triangle ABC. So I notice that angle A is 90 degrees, so I'm going to just draw a random 90-degree triangle. I'm going to label this ABC, label my 90-degree angle ABC. Little b is 12, so this is 12 down here, and little a is 21. And I feel like we've already done this triangle, haven't we? 12, 21? Yeah, 21, 12. So there. So we already have our solutions. So that's the thing that you can rely on as well. The person that built this this worksheet loves Fibonacci numbers. So they're using 21 a lot. They're using 55, 34, 5. So similar to me, they share those things they like. So now when it says solve the triangle, what is the missing information that we want to solve so that we have effectively done it? Tell me, what information do we need to add to the triangle here? Do we know this yet?
Yes.
No, so we need to find that. Do we know this yet?
No.
Do we know this yet? No. So we label them, and then we know that we have to go find them. Okay? So x should not be hard to find. How do you want to find x? Do you want to find it with Pythagorean theorem or using trigonometry? Trigonometry? Great, because we've done Pythagorean theorem examples before. Just look at that and know you could use trigonometry here. So to use trigonometry, we need some angles. So let's go ahead and find some. Sine theta, I know, is equal to opposite over hypotenuse. I always start with that. And then I notice, hey, look at that. From angle B, I know the opposite and I know the hypotenuse. So that's what we're going to work with. Sine B is equal to 12, 121, which happened to be equal to 4 on 7. And then we take the inverse sine of that. So beta is equal to sine inverse 4 on 7. And we're very happy. We can punch that. 4 divided by 7 equals this. Take the sine inverse of that. Tells me 35 degrees again. So beta equals, we're going to be using that because we're going to want to use these two angles to solve for that. So let's keep a little bit more accuracy. We want to reduce the amount of error that we have, so we're going to keep 34.85. 34.85 is a lot of detail. Why do I put the 8 there? 34.85 is what we're calling that angle. Okay? So now let's improve our diagram and put that on there. 34.85 degrees. So much detail, Mr. Jennings. I can't believe we're being so accurate. All right, and then we're going to use that to solve for angle C. We can use trigonometry, but we can just use A plus B plus C equals 180. So let's do that. 90 plus 34.85 plus C equals 180. Oh, look, 90 plus 34.85. I know how to do that. That's 124.85 plus C equals 180. All right? And then once I've got that, I know exactly what I need to do because I've just got these strong algebra muscles. I just subtract that from both sides. $55.15. Of course, it's 55 degrees because it's the Fibonacci lever. So C equals 55.15. So there we go. We've got this beautiful diagram now with all of the angles solved. And now we want to use trigonometry to solve for that. It was a good choice. How would you do it? How would you do it? How would you now use trig to solve for that side?
Now you wait, I have
Yeah?
34 and then 55.
What?
Do you use the 34 and the 55?
Not and, or. You use the 34 or the 55. Either one will give us the same information. So which one do you like working with?
55.
Okay, so what trigonometric ratio are we going to use in this case? It better involve the opposite. You want to use tan? Let's use tan. Sure, let's use tan. So we're going to go tan theta equals opposite over adjacent because SOHCAHTOA told us so. And then we go ahead and we sub in tan 55.15 equals x over 12. multiply both sides by 12 to isolate x. See, strong algebra muscles. So nice. And then we just punch it. 12 tan 55.15 equals x. Watch this trick. I still have that up on my here, so I go trigonometry, take the tan of that, and multiply it by 12. And we find that it's 17.23. Okay, so x is equal to approximately 17.2. There. That's how that do. Yeah?
Actually, wait.
Wait on waiting?
So it's literally the same thing as the one on the first thing. But then
Yeah.
why is 12 so, like, why is the, like, bottom one so much longer?
The solution?
Like, okay, the triangle on the other side, that was, like, the same as it.
Yeah, same triangle. Yeah. Here we were asked for one piece of information. We found the one piece of information and we did this. But in the next one, we were asked to solve the triangle, which meant we had to find all of the extra information.
Yeah,
So we had to use a variety of tools. Like we could have used Pythagorean theorem. We elected not to. We used trigonometry. We used a plus b plus c equals 180 to find the other missing angle. So we did a lot of stuff there.
But it's basically the same triangle, right?
It's the same triangle.
So then, why, so the x is like 17.2,
Yeah, that's the missing side length.
but then why is it so
we
much
didn't-
smaller than the 12?
17.2? Oh, because the diagram's terrible. Yeah. The diagram, my diagram is only there to get my algebra set up right. It's not there as a kind of model of the problem. The diagram doesn't need to be, one of my pet peeves is people who let's say it's a math teacher problem and it's a math student problem where people get really fussy about their graphs and their diagrams being like super hyper accurate. When actually what we want is a picture that helps organize our thinking and get the math set up right. So this picture set the math up right. After we did that, we could then create, like we could even model in a computer some really accurate diagrams using these side lengths, using these angles, and really see the triangle very beautifully if that was important to us. Yeah, so that's a good question. And the other thing is like this was a much more involved process because up here we took the car to the garage and we said change the oil. Down here we said change the oil, rotate the tires, and do some car detailing. Like there was just more on the list of things, jobs to do here. That's the only difference. Okay, try these textbook problems, and by popular demand, I will make the Delta Math available immediately for these two topics, so that you can start working on that now if you like.
Okay, so I really wanted the answer before.